we're live and in color. So for those of you who are looking at this virtually, hey Ty, looking at this virtually, we're going to go through what we typically do as an MTA study session. This is to prepare for those who are here locally. Thanks, Jen. To prepare for that badge, that certification exam. It's a fundamentals, networking fundamentals, and that's it, okay? So even though if I don't look at the camera, I'm probably looking to my students here. If you need to ask me questions, your face isn't being recorded, but your sound, your voice is. So as long as you're okay with that, then you should be okay with that. If not, then stay quiet and I don't want to ask you anything. So my name is Dr. McNally. I'm the instructor here for the MSSA program in Norfolk, and let's get started. So what do you need to know? This is purely fundamental. It doesn't, what you're looking for is just that. It doesn't go beyond the basics. But there are some things that you should know and know well enough so that if you see that type of question or a variant of that question on the test, you could answer it successfully. So we have something called the OSI model. The OSI model or the OSI reference model, it's the same thing. The OSI model has 7 layers. 7, 6, 5, 4, 3, 2, 1. The OSI model teaches us, tells us, shows us how two devices communicate, both at the very physical nature, literally plugging things in. We've got this blue cable down here. This is a Cat5 Ethernet cable. It could also mean Wi-Fi, and all of you probably are familiar with Wi-Fi. Then from there, we're going to talk about more abstract concepts, you know, how things are actually labeled, I guess is the good way of putting it. What goes on top of the data in order for that data to get from point A to point B. Okay, so when you get that, you can understand how, you know, an email is sent, or how files go to a file server and all that kind of stuff. Okay, so let's give this a shot. I'm going to write down these letters for the test. You will have to know what the name of the layer is and what number it's associated with and what's going on there. Okay? So I'm going to write out some letters. Okay, so there's a couple of mnemonics, ways of remembering things that typically work for some people. I'm going to show you 2 of them, and if you are creative enough, you could make your own. So we have the letters A, P, S, T, N, D, P. All people seem to need data processing. As you can tell, it's purely IT related, but it seems to work. So all people seem to need data processing, and in that order, okay? Going up, please do not throw sausage pizza away. Whatever works for you. If that doesn't work, make something up. So let's figure out what they mean. If I make a spelling error, it's there for posterity's sake because we're being recorded. But if you see something and I don't catch it, please let me know. Okay, so we have the physical layer. Everything in the computer world is binary. What we call bits. And bit is short for binary digit, okay? Binary meaning it's a numbering system, 0 or 1, off or on, true, false, that's it. So we have zeros and ones. When zeros and ones get put together in a certain way, they actually represent a letter or a number. So this way, things actually can be transmitted from place to place, but they get transmitted in code, zeros or ones, okay? So like I said, this is the physical layer. It's the actual physical cable, the electricity flowing through this cable. It's also the Wi-Fi. That would include Bluetooth capabilities. So it's the actual transmission of data, physical layer. Let's see if I can draw it over here. So I'm going to try to keep this level. We got our payload, so this is going to be our data. Okay, we need to get this data from point A to point B, but this is it. This is our message. Okay. So far so good. Okay, cool. Data link is the next layer up. You seem to have smiles, so you know all of this stuff already.
I would say I'm familiar with the.
Looks familiar?
The layers. I
Okay.
just want to get familiar with what exactly they do, like on the master data.
Okay, let's get more familiar with it. Data link. So we have our payload, and now we need to be able to move it. But in order to move something from place to place, from machine to machine, we have to have a way of understanding, one, how to identify where a machine is and what machine it is, and then how to identify what protocols are being used, where in a network that address is, and so forth. So I usually give my story, and my story focuses on my grandmother. So now everybody in the world, because we're being videoed, will know about my grandmother. We know that, well, I'm 50 years old, and so back in my day, we actually used mail. Snail mail it's called now, and it's a little envelope, and you put a stamp on it, but you address it, right? The center of the envelope gets the sent to or destination address, and up in the right-hand corner, at least in America, I'm not sure about the rest of the world, up in the right-hand corner is the return address, where it came from, the source address, okay? In order to send things from point to point on our computer networks, they need addresses too, okay? So here at the data link layer, we're going to use something called a MAC address. And MAC is short for Media Access Control, so it's a MAC address. A MAC address is hexadecimal in nature. So hexadecimal versus binary. Hexadecimal is base 16. Base 16, so this is an example. But what we're concerned about for the test is that this MAC address is 12 characters long. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. It's 12 characters long. And each one of these characters can be 0 through 9, or the letters A, B, C, D, E, F. So 0 through 9 is 10, 11, 12, 13, 14, 15, 16, base 16. There are 16 possible combinations for each one of those characters. Okay? So I could literally have C, A, 3, 6, F, 0, 4, 5, 7, C, and so forth. Okay? But that's what it's going to look like. The first 6, this may or may not be on the test, I'm not quite sure how fundamental this test gets, are vendor specific. So this is going to identify the vendor of the NIC card that produced this. Okay, so let's talk about something real quick. Where would you find the MAC address? And this is where, if you're going to become an IT professional, you have to get accustomed to using abbreviations. We use abbreviations for everything. Everything. So right there, there's one, that's a MAC address, Media Access Control. We have something called a NIC card, Network Interface Card, okay? Or if you're, Network Interface Card. If you are on a physical machine, whether it be laptop or desktop, laptop and desktop, as you know, is tower and all that kind of cool stuff. This physical blue cable that I keep on pulling up off the floor has to be plugged into something. It plugs into the NIC card, okay? That's what this is. So it's a circuit board that connects to a piece of physical equipment, and on that NIC card you'll see, well, you won't see it, but there is an embedded, what we call burned in MAC address. It's associated with one NIC and one NIC only, ever. So if this NIC gets destroyed, so does this MAC address. It's gone. It's only associated with one. So it's a one-to-one relationship. This is where you would find it. If you go into the computer and you're going to learn about something called the command line or PowerShell, these are our administrative tool sets that we're going to use in class. If you type in the search feature in CMD or PowerShell, this is PowerShell. You would use a basic command. It's called ipconfig. That's probably on the test. ipconfig. Type in that command at the prompt in either one of these interfaces, and you'll get a MAC address. You'll get other information, but you will get what's called the MAC address. And actually, we use a couple of different terms. It can be called the hardware address or the physical address. So the hardware, the physical, and the MAC address all say the same thing. Okay, so hexadecimal is 8 characters long. Each character is 4 bits. So if you're asked how many total bits are in a MAC address, 4 times 12 is 48. That's another possible question. So 4 bits per character, 12 characters, 12 times 4 is 48. That's if my math is still good. I think it is. Okay, so the key takeaway from the data link layer is the fact that there's a basic physical machine address, okay? And we call that a layer 2 address, okay? So again, OSI layer 2. If you're asked what the layer 2 address is, it's the MAC address of that machine. Hey, Carlos. Oh, I'm progressive. All good so far? Okay. I'm going to do some erasing because I only have so much board space to work with. Now, is that the only thing that's in the data link area? No, it's not. But for what you need to take away and pass this test, that's what you need to know. So let me redraw this payload part. I'll call it P, and this is going to be our data area. Now let's hope I can get this all lined up. Back when I was in school, and we still used chalkboards, my teacher had this thing, so you remember, and she ran it across, so we got all these even lines. I need to get my yardstick. Anyway, we got this payload. We need to send it somewhere. So we need things such as headers, and we're going to put a header in front of the payload, and that's going to tell the machines what to do with this payload. Okay? We're also going to create a trailer. header and the trailer. And at the layer 2 data link layer, we're going to have something what's called a frame check sequence. Because when we send data from point A to point B, anything could happen. It's running over some electricity, so there can be interference. And if interference happens, that data that's been sent can get what we call corrupted, and it will basically crash and die. It won't get to where it needs to go. In order to protect someone against that, we have something called a frame check sequence. For example, you need to send data to you, and I'm using you because names are going to be difficult in 2 hours. However, what you sent, the machine has to be what's received by this machine. And the first place to check is here. Because the issue is one of security. If you send something to you, both of you people and the machines, want to make sure that what was sent is what's delivered. And this is going back to my grandma. And I'm going to add my grandma story as we go. My grandma sends me a $100 bill. She's been doing this all my life. On my birthday. And my birthday is in August, so that's coming up pretty soon. She sends me a $100 bill, right? Now, and she still sends it by mail, so it's still, at this point, it's a $50 stamp. It's a 50-cent stamp, so that stamp keeps on getting more expensive. I remember it was like 10 cents. She wants to make sure that I get that $100. I give it to my daughter, I don't keep it. But she wants to make sure that I get that $100, right? But anything could happen in the mail. You know, somebody, it could get lost somewhere. Somebody could steal it. It can fall into a trash can. Who knows? Okay. Well, there needs to be a way of protecting against that. When we send electrical information across lines, it can be interfered with. One of these zeros can become a 1. One of these 1s can become a 0, or more than 1. That would mean that something happened to the, what we call the integrity of the data. So what's going to happen is this is going to be a hash. This is a bit beyond what I think you need to know, but there's going to be what we call a hash value that's going to be associated with the data that was sent, and the algorithm that's going to check for that hash value, it's checking to see if this hash value is the same. If even one of these bits flips from a 0 to a 1, the hash value is going to be completely off, something completely different. And that's going to tell this computer not to trust the integrity of the data. And then that computer is going to say, please send that data again. It won't even open it. It'll just drop it. So I can't trust it. Okay? That's what happens first. In order to get there, we're going to put the header and we're going to put the MAC address. So there has to be a first layer header address information. In order for something to be sent, just like I said, my grandma sends me my Christmas card, my birthday card. There's 2 addresses, source and destination. So there has to be both the source and destination MAC addresses at this header, on this header. And there's more information, but you need to know that there's source and destination. Both have to be there. I'm going to add this because I don't want to forget it. There are also pieces of equipment that are associated with the layers of the OSI model, and you need to know at least 3 of them. Now I'll explain, we'll come back to this after we go through the OSI model, because I'll draw a diagram, what we call a topology, and so that you can kind of see the pieces of it, okay, and understand how they work. But at the physical layer, we have what's called a hub, okay? And a hub is just a device that you plug things into in order for one machine to talk to another machine. And that's it, okay? It doesn't understand any addressing, okay? It just receives data and sends data, kind of just repeats it, okay? The switch uses MAC address information to forward data. So a hub will receive information, receive some data payload, and out of all of its other ports will send out that data. The best we had when we had it, but it was a security breach because you don't want all machines receiving data that's only appropriate for one machine. So the technology improved, and then we created the switch, and that switch allows us to forward information based off of the MAC address. And because MAC addresses sit at layer 2, we call a switch a layer 2 device. Now, you may already know, I don't know what your knowledge is at this point, but there are what we call layer 3 or multi-layer switches. That's out of the conversation, that's out of the discussion for this, where you are right now. Your goal is to pass this MTA and get in my classroom. So these things do exist. They're beyond the scope of what we need to cover. Okay. So if anybody talks to you about, or if the test asks, what OSI layer will you find the switch? It's OSI layer 2. That's where it's going to sit. Okay, let's move on. We now have the network layer. We have to talk about some more addresses. We need to talk about IP addresses. My coffee's already cold. All right, so we know that MAC stands for Media Access Control. And this is going to be the most popular set of letters that you will become familiar with. And it's called Internet Protocol. Internet Protocol. So it's an IP address or Internet Protocol address. Now we need to spend some time breaking what an IP address looks like. But right now, excuse me. It's in what we call a dotted decimal format. Dots and decimal numbers, so it's dotted decimal. Each one of these is what we call an octet. An octet has 8 bits. An octopus has 8 arms. An octet has 8 bits. So there are 8 bits here. Again, 8 zeros or ones. 8 bits here. 8 bits here. 8 bits here. So that means that the total number of bits in an IP address is 32. Now, I'm not quite sure, but I don't think that this level of testing will talk about a different type of IP address, because we need to know 2. There's what we call IP version 4, it's what we're still using, and it's the dot decimal format. There's IP version 6, there are other versions, but these are the 2 that are prevalently used and that we use now. IP version 6 has 128 bits, it's extremely long. It's in hexadecimal format, and it's beyond, right now, it's beyond the scope of our discussion because we talked about it actually in class, but none of it does exist. So it's hex in nature, it's 128 bits, and I'm pretty sure that if you're asked anything, that's all you're going to be asked, because it's a bit more complicated than a fundamental level, and this is a fundamental exam. This is dotted decimal, and it's 32 bits. And like I said, we're going to break this down after we do the OSI layer, because this is functional to what it is you need to know. This is the crux of our existence in the IT world. Okay, both of these. Okay, network layer has an IP address, dotted decimal format. This is what it looks like, 32 bits. Let's add to our payload. For those who are here, if you have any question and I need to go over something, please tell me to stop and do it again. I'm sure our listening audience or our watching audience will appreciate that. So this is the same payload. This is the same trailer. This doesn't change. We're just going to add to the header information. Now, I'm giving you the, go ahead.
So, when you said that the IP address has, each hotel has 8 bits.
8 bits per octet.
Every time I see it, an IP address, this is how I see it, right? It's like either a combination of 2 numbers or 3 numbers.
Yeah, we're going to break the IP address down. We're going to get into more depth after I do this part.
Okay.
Yeah, because you need to know what it looks like, and there's classes, and there's siders, and there's all kind of more. That's just a start. That's kind of say. That's just to say that there's what we call a MAC address, and that's associated with a physical machine. It's on the NIC card. Okay. That I'm trying to determine how much of the discussion we should get into depth, so I'm not going to go that deep. This used to be sufficient for our needs because we would get computers from the vendor, they'd be in sequential order, we could group them together real easily, and we could communicate. But as networks grow larger and we use equipment from different vendors, it becomes difficult to group things together. And we need to group things together because a group such as the 4 of you may need to be put on a project and have your own set of resources, right? And then I might have a group over there in another classroom. I need to put them on another network because they're doing something else. And I may limit, I may want to limit, and I may need to limit the sharing of resources, okay? So I'm going to put you on different networks. That means I need to group you in different ways. We do that through what's called the network IP address, which is also called the logical address. This we said is physical. This is associated with the NIC card or the physical machine, and it's always going to be associated with the physical machine unless you swap out, literally swap out one physical NIC and put another physical NIC in there, okay? The logical address can change. So you can have a computer sitting in front of you that's in a network in this classroom. I could literally take that physical computer and put it anywhere else that I want to and change the address on it and put it in another group. So that's how valuable that is. So in order to transmit data from point to point, I need to have both sets of addresses. I need to have the source and destination, where it's coming from, where it's going to, of both the logical and the physical address. Without any one of those 4, I can't send data. I need to have all 4 before any data gets sent. So the header information now has the IP address information and the MAC address information. Now, at this layer, layer 2 of the OSI, we have what's called a frame. Like a picture gets framed. The payload gets framed. It gets a header, gets a trailer. So we call it a frame. So if you hear any reference to what a frame is, it's the layer 2 word we use to identify this piece of information, header, payload, trailer. When we get up to the network layer, it's called a packet. Now this is the most prevalent or most used word that we talk about regardless really of where it is on the OSI layer. We talk about sending packets. And this is where it comes from. Once you add the network layer information, it's called a packet. However, in the IT world, even if it's down here, we probably still call it a packet. We rarely use the term frame, but in order to pass the test, you need to know that this is where it comes from. So at what layer of the OSI model will you see a frame? Layer 2. And then of course, at what layer of the OSI model will you see the packet? Layer 3. That's a U. That's a router. So a hub does not use any addressing to make its forwarding decisions. It just receives data and sends data out all other ports. A switch will receive data and send it out only the port that has the physical address associated with it. And a router works at layer 3. That means it separates networks. So if I have this network over here, whoops, and this network over here, whatever they are, I have to separate them by a router. It's just the device that we use. Okay? And in order for anything in here to get to anything over there, the router needs to know, based off of IP address information, that this network is associated with this physical port and the other network is associated with the other physical port. And we'll get there, but you just need to conceptually to understand that we're differentiating. Okay. Hub switch router, packet IP information. A router does two things. It forwards packets and it separates networks. That's its two primary things. It also filters data, but that's a bit beyond the scope here. Now, hopefully I won't get in trouble for this, so it's going to be out there for posterity's sake. But you may be asked a question. See, I get fired right now. You may be asked a question as to which layer does routing take place. Routing meaning to send data from one network to another. And depending on who's asking that question, depends on what they know. But because the router is associated with layer 3, routing occurs at layer 3, fundamentally. However, if you were to be asked or ask a network engineer, somebody who works at Cisco or builds networks and whatnot, they're going to say that routing occurs here. At the transport layer. Because this is where your routing protocols sit. Okay, so we have something called transport layer protocols. We have TCP and UDP. TCP and UDP. Transmission control protocol. Transmission control protocol. User datagram protocol. These are umbrella type protocols with other protocols sitting underneath them that fundamentally control how we move data from point to point. Transmission control protocol is a protocol that requires what we call an acknowledgement. We call it an ACK packet, an acknowledgement. Meaning that, I'm going to go back to my grandma. Now I already said that my grandmother's going to send me, because she has all my life, at least as far as I can remember, she's going to send me a $100 bill in the mail. Now, what do you think my grandmother, who is in her 90s at this point, is expecting from me when I get that envelope? She's expecting a phone call. She's expecting an acknowledgement. She wants to know that I got what she sent me. Okay? Transmission control protocol is that type of protocol. It wants to know from the destination machine that it got what the source machine sent it. And that means that an acknowledgement packet is going to come back to the source machine and say, I got what you sent me. Could you send me more, please? Okay. So that's what's going on. User datagram protocol does not require the acknowledgement. That means that the source machine is going to send, and it's not going to be requesting an acknowledgement packet every time it sends something. So primarily what you should be concerned about is we're going to use user datagram protocol for two services. For video, streaming, and for voice communication. So if you ever streamed a video or was in a video conference, there are machines talking to each other. Or if you're on a digital network, and you pick up a phone, which is called an IP phone. It's a small computer, it looks like a phone, but it's really a computer. And you start talking with it, it's not requiring the acknowledgement packet every time you send out your voice or that video. Now, this is where the human people come involved. If the two of you are talking on a digital network through a voice communication system, and you don't understand what was said, the computer, your phone doesn't care. It might have been jarbled. It's your responsibility to say, could you repeat that again? If you're watching YouTube, which I do a lot, like I said earlier, I've got a YouTube channel. So I produce content and I view content, and there's a fire truck outside. It's not important for you. It's not important for us. It's important for them. If you're streaming a video and it buffers and you're not getting it, or it stops for some reason, the computer doesn't care. The computer that's in front of you doesn't care. You may care, so you may have to refresh something and take care of that. But the computer itself doesn't care. And the computer sending it doesn't even know. It might not even know that it's been interrupted. It's going to send. And if it stops, it stops. It doesn't care. Transmission control protocol requires the acknowledgement. UDP, user datagram protocol, does not require that acknowledgement. All good so far? Mm-hmm. Now, I said that routing occurs at the transport layer because we have something that works with the router. We have something called routing protocols. Now, I'm not quite sure, to be quite honest with you. It's been a while since I've taken the MTA. But routing protocols may be routing information protocol, RIP. Doesn't matter if it's version 1, 2, or 3. Routing information protocol. We also have something called intermediate systems, intermediate system, ISIS. These are routing protocols. And what you would do is configure the two connecting routers with the same protocol in order for them to exchange what we call routing table information. They're going to exchange the information in the routing table. The routing table is where the router stores all the networks it knows about. Okay? So if it has several networks associated with it directly, they're in its routing table because you've told the router what's connected to it. And then if this guy has networks associated with it, these two will start talking. It's like, I used to live in North Carolina. That's all we did in the summertime. We go in the backyard and we all be connected by fences and we just talk. What's going on with this neighbor down there? What's going on with this neighbor down there? What's going on here? We just talk. So that's what the routers are doing. They're sharing routing table information. Everything that they know about every part of the network they know about, they're sharing. We also have EIGRP, Enhanced Interior Gateway Routing Protocol. Again, another routing protocol. Open shortest path first. I'm not quite sure if this is specific to your text. I'm not even sure if it's in your study material. If it is, then understand that these are routing protocols. You configure the router with one of the routing protocols, and then the routers talk to each other, and they just share information. So it's a routing protocol, sharing routing table information. Okay, what happens here is network administrative type duties. People with CCNA, Cisco Certified Network Associates, CCNP, Cisco Certified Network Professional, these are the people that build the infrastructure that allow all of our data to work, to go from point to point. They're creating this kind of stuff. Their job is to make sure that all the infrastructure works. A systems administrator, it's more like, a systems administrator is up here, and what happens here and here kind of varies. But for test purposes, that's the session layer. This is the presentation layer. And then finally we have the application layer. For test purposes, what happens at the session layer? The session layer controls starting a conversation or starting the transmission of data from point A to point B, monitoring that transmission, and then what we call terminating, or stopping the transmission. Every transmission, once the final packet's been sent, that open form of communication, that open communication link between point A and point B, has got to be stopped, otherwise it's a security risk. So the session layer protocols are responsible for starting, monitoring, and stopping the transmission between point to point. What time is it?
9:47.
9:47. Do you guys need to stretch, run around, do jumping jacks? Because I don't want to bore you to death. But you all good? Okay. For test purposes, the presentation layer is responsible for encrypting data. Now, not a big part of the scope of knowledge at your level, but encryption is simply a way of taking what we call plain text data, something that we can physically, visibly see, and changing it into gibberish that we couldn't make heads or tails of. Encryption. Okay? So, if you're sending stuff, data, to point A to point B, and just in case you get hacked and it gets stolen, you don't want anybody to figure out what it was. So you would encrypt it. And then she would have an algorithm that would, of course, decrypt it. And then the application layer. This is your user interface. And so what we learn in the MSSA program is all the application stuff, such as DNS, DHCP, Active Directory, all that cool stuff that actually has value to the user and to the machines, not the infrastructure stuff. Like, where am I going to put where am I going to store all this stuff? Where am I going to put all my data, right? So we need storage. We need to be able to access that storage. So we need to be able to create folders and shares and things like that. This is all up here. We need to be, the larger your network is, the more tedious it would be for one of you as an administrator to go in and put an IP address on literally every machine. So we have a service that does that. It's called DHCP, which we'll talk about in a little bit. But your responsibility as a system admin to create those applications, to set up the application that says, okay, I want a service, I want a machine to do the job for me. So if I plug a machine into a network, a domain, it needs an IP address, because we sit down here without an IP address, it's not going to communicate with anybody else in the network. So we have the service to do that for us. Domain name service, or domain name system, DNS. At this point, everybody's been on the internet, the World Wide Web. You don't type in an address, do you? I don't think anyone has ever typed in an address in the text box that the URL says. Go to MLB.com, NFL.com, Yahoo.com, MSN.com. You type in words. The computer doesn't understand a word. It doesn't literally understand what you're talking about. So that word, that name that you put in that text box has to be translated to an address. And we do that through what we call the DNS system, domain name service. So this is where you're at, or you will be at in a couple months, in setting up all these services so that your end users, those employees that need to do their job, can do their job on the machines that you put in front of them. Okay, so that's the OSI model. And even though I stopped there, you have to understand that with each layer, there's a new packet, header, that has the specific protocols that are assigned to whatever it is you're working with. So when we go up this ladder, you'll have transport layer data, the routing protocol information. You'll have session layer data in the header, which talks about, I need to open up a session, I need to monitor that session, I need to close that session. If there's any encryption going on, that's in that header. And finally, what applications are being used. So let's erase this part. Let's get into the fun stuff. Let's talk about the IP address. Now, even if it's not on the test, and I talk about it, and it's not on the test, or even in your study material, it's relevant to coming into my classroom, because everything I talked about, you should have knowledge of before you get in there. That's it. Okay, so I'm only going to talk about IP version 4. This does not cover IP version 6 at all. You need to break down IP version 4 so you understand the mechanics. Okay? You really need to understand the mechanics. Like we said, it's a dot decimal format, so I'm going to draw out 4 lines. Well, I'm actually going to draw out 3 lines I'm not even going to do that. I'm going to do something a little bit different. I'm going to talk about classes. Because this is fundamental. We don't categorize IP addresses by class anymore because we have different technologies that help us with class-less information, but it's still testable. I have no idea why, because it's so archaic in terms of its functional element, but it's still testable. So we have things called Class A, Class B, and Class C. These are your testable elements. Now, there's also a Class D and a Class E. You need to be able to recognize a class based on its IP address. So if I give you an IP address, you can easily say, well, that's Class B, or that's Class C. You need to be able to recognize it, and that's what you're going to be asked to do. The class is identified by the number in the first octet and the first octet element. Simple enough. 1 through 126. Right? All right. So he agrees with me. I feel better. I feel better now. All right, smart Alec. How do you identify Class B?
I know it's 128 I'm not sure.
I'll give you a hint. First number is a 1.
Yeah,
You got it?
I do have it. It's class.
You got it?
191.
Yeah. So, 1 through 126. If you see that in the first octet, it's Class A. 128 to 191. If you see that in the first octet, it's a Class B. Then, regardless of any other information, whatever the mask is or the decider is, it's still that class category. Okay? But, like I said, it's testable, but it's archaic.
$192.
192, right?
223.
To 223. Okay, let's see if my memory holds true. 224 to 238. I hope that's true. What? 239. Is that what the Google says? And then 240, 255. These are not testable. You might be tested on 224. 224 is a multicast address, which you will see as a network admin or a systems admin. But for purposes of D and E, it's going to fit in D.
Why the Class B doesn't go, doesn't start at 127?
I don't know.
The other ones are 200.
Hold on to that. I'll get to it. I will get to it. I promise. Let me finish this up, and then we'll come back. Okay, so this is what you'll be tested on. Class is identified by the first octet. Now, there are some default values that if you're not told anything else, you make these assumptions, and these assumptions are safe. I'm just putting these X's because right now they could be any number. And we'll clean it up in a little bit. By default, that means if you're not giving anything else, and this is kind of where the class information becomes relative, that if you have a, let's give this a 10 for the sake of argument. 10.0. Dot zero. Okay, we know that that's a Class A. We look at it, okay, that's a Class A. Okay. Class A is going to have some default information. So every IP version 4 address is going to have what we call a mask. And the mask is going to be the network identifier. It's going to help you determine what network ID is appropriate for that address, or what network this is. Okay? This, the mask and the CIDR, they say the same thing, they say it differently. They tell you the same information. They just tell you it a bit differently. A CIDR is going to be a slant value. It's also called a prefix, in case you hear that word. Slash, slant. But for class A, it's going to be an 8. Okay? Now, what does that mean? It means this. It means that there's going to be an IP address, and then there's going to be a mask. There's going to be another section of dotted decimal information that's going to follow the IP address. And that mask is going to tell you how many bits are on related to the network ID. And for this, it's the first 8 bits. 8 bits, 8 bits. Now, we haven't figured out how to get there yet. We will, because there's a whole binary system you have to learn. But this and this say the same thing. They just say it differently. This looks different than that, but they're telling you the same information. The first 8 bits are on in the dotted decimal mask, and that means that the only octet relevant for the network ID is the first one, the 8 bits here. That's the 10s. This is now the 10,000 network, if and only if this is true. So that's the network ID. There are about 4 million some odd, if my numbers are correct, it's been a while. It could be more than that. 4 million potential IP addresses, because this octet, and this octet can be used for IP addresses in that network. Okay? So it's big space, big span space. Every network has a starting point. Every network has an ending point. This network ID is the starting point. And it is that. This is classroom 7. That is the ID for this physical space in this building, number 7. I can't use that number 7, theoretically speaking, to identify anything in my network. Okay? 10,000 is the network ID. I can't use the 000 to identify any machine or interface in that network as part of that network. It simply identifies the network. I can't put it on a machine. In the same way, my broadcast is another IP address in that network, always going to be the last IP address in that network. I can't use this address to put on any machine because it's a broadcast. What's a broadcast? A broadcast means that if I need to communicate from one machine to every other machine on my network, I will broadcast it, just like it was in the stadium. One person telling everybody, broadcast. So in order to do that, I would use this IP address. And so I can't put this IP address on a specific machine. So a network will have some key features. A network will have a network ID. It will have a mask insider associated with it. It will have a broadcast. And then everything in the middle, everything between this address and this address is what's called the range. Everything in the middle. So everything from 2.001 all the way to 10.001 to 10.255.255.254 is the range. Lots of addresses. Okay, so default values. The mask may be called a subnet mask, net mask, or mask. It's all the same thing. Default for Class A, 255.0.0.0. Default for Class B, two five five 255.0.0 slant 16. This is telling me that the first 2 octets, all the bits are on. First 2 octets, all the bits are on. This then identifies my network, 172.16.0.0. As long as, if and only if, my mask is 255.255, the default method. If this at all changes, then the values here change in terms of the ID. The broadcast is the very end, 172.16, fill it up, 255.255, and the range is everything in the middle, between this and this. Basic stuff. I just want you to get comfortable knowing that I now turn every bit on in these 2 octets in my mask, which then evaluate to where would I find my network. That's all I'm saying. Okay. One nine two 168.10. Mask 255.255.255.0. 3 bits, 3 octets all the way on. Default's 255. For B is 255.255. C is 255.255.255. Slant 24. My network is 192.168.10.0. My broadcast is 192.168.10.255. And my range is everything in between that and that. You probably won't get asked, because this is fundamental, you probably will be asked stuff here in terms of network concepts. You may be asked if you see this or an address, what class it's in. You may be asked that if it's this class, what's the default mask or CIDR? So these are the types of questions that you'll get asked on this type of test. This test is purely multiple choice. You're given a straight up question, A, B, C, or D. Pick the right answer. There's no tricks here. This is very, very basic. You will not get asked anything here. It's beyond the scope. But you know for every network there's an ID, there's a broadcast, there's a mask insider associated with it. These are the default values, and the range of addresses is everything in the middle. Okay, let's break this down even more. The only thing I'm going to break down is the 192.168. However, one of you asked about the 127. 127 is not identified as a addressable range because we call it a loopback. everything inside that range of address from 127.0.0.0 to 255.255.255 fits into what we call a loopback, which means that you plug a machine in and you run the 127.0.0.1. It goes into the network, connects to the switch, comes back to the machine. If that works, then you're physically connected. It's a way of testing your own connection into the network. That's all it is. That's why we don't address the machine. So, but if you're asked, what range of addresses in my loopback? 127.0.0.0 to 127.255.255.255. That's your whole range with your network and broadcast. So it's everything from 1 to 254. But the default, usually when the loopback is, you'll test it with 127.0.0.1. You'll test your own connectivity to your own network. To test connectivity from one machine to another, you're going to, what we use, the ping command and the other address, 192.168.10.5, to test it. But we'll talk about that. Okay, so let's get an address up here. 192.168.10, oops. That 0, this is going to be our starting point. If you guys need some water, I got water up here. Caitlin's going to starve us, so we don't have any food. But it's almost lunchtime. Okay. First octet, second octet, third octet. 24. So, not touching it. I know that what here, 1, 2, 3, 1, 2, 3, that's my network. I'm in the 192.168.10.0 network, slant 24. I can't touch anything here in terms of IP addresses. I don't need that. You didn't hear that. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits in an octet. Binary numbering system, base 2. I'm going to show you where we get all these crazy numbers. Hopefully you all remember math from grade school. 2 is my base number. I've got exponents. This system never changes. Doesn't matter which octet I'm in. I've got 8 bits per octet. Base 2 because it's binary. Exponents 0 through 7. 8 bits. Hopefully you see that. Each of these binary numbers has a decimal value. Yep, yeah. Always 1. Always itself. 2 times 2. 2 times 2 times 2. 2 times 2 times 2 times 2. You get the idea. This pattern doesn't change regardless of octet. But it's from this information that we get this, regardless if it's the address or the mask. That's how we get it. So if you see this, and for those of you in my virtual world, if you see this, you got to memorize it. Because this is the foundation of everything we do in Active version 4 world. And it doesn't change. That's what's so cool about it. But it's dead because we're moving to IP version 6 because too many things need to be connected to the internet, and this only has 4.4 billion? I have to ask my class, I forget. I think it's billion addresses altogether, and we can't use them anymore because they're all used up. But we need to get some information from this chart. I call this my chart. because it always works. Because if you want to go into take your Security Plus, if you don't have it, your CCNA or your Network Plus exams, this is fundamental. Okay, and these exams are timed, just like your MTA exam is timed for hour and a half, 90 minutes. Is that right?
I think so.
Yeah. So, and every exam is timed. So there has to be a way of, if you don't have it, you have to have a system of getting to the right answer rather quickly. This is a system to break down your IP information so you can get to the answer rather quickly. Now, if you take the test at home, you're on your own. I mean, you literally scan your little webcam all over the room. Your dog, nothing. You can't even have a bug in there because you can't have nothing on the desk. Just you in front of the computer, and you can't move your eyes. You just gotta look straight ahead. But if you take it to a testing center, you have more leeway. I mean, you're not going to be looking at the person next to you, but they're going to give you a scratch pad or a dry erase pad, dry erase marker, so you can write quick notes because they're going to be monitoring that. But you can't do that at home.
Where is the?
Pearson View Testing Center?
Mhm.
I don't know. I don't know Norfolk. I mean, I go to Chesapeake, St. Leo's. So St. Leo's is a testing center. Y'all know any of the testing centers?
Yeah, there's.
I have to ask my class.
Yeah, there's one in Virginia Beach called Intellect Tech. That's what
Okay.
I'll be taking it next Friday.
Okay.
So,
So there's a couple of them. I could always pull somebody from my class to ask. I always go to St. Leo's.
If you do it,
'Cause I like to
online,
test
you're
it.
gonna have a proctor.
Yeah, someone's gonna be watching you through your webcam.
Okay.
That's what I said, but it's scary because if your network, if your network, your ISP goes down, your computer crashes, whatever, you lost. That's a fail. Whatever happened. So, but if it happens at a testing center and somebody
You're
technically,
responsible for it.
yeah, you get a free retake. Yeah, so it's kind of I always go to a testing. I always suggest go to a testing center because if anything would happen other than you cheating, technical wise, you get a free retake. Okay, we need to acquire the same information. So I need to get to the mask, and I need to get to the cider per octet. Okay? So we already know my cider right now is 24. But this can actually change. Okay? In case nobody asked the question, but that's another acronym.
I'll
Ask me the question then.
What's that stand for?
Classless interdomain routing. Classless interdomain routing. So what does that mean? We talked about classes A, B, and C. They used to be handed out a long time ago in a galaxy not too far away as whole classes. Well, that became inefficient over time because we just kind of use things. So there has to be a way of breaking things down into smaller pieces or usable pieces. I might not need all the IP addresses in this network because I might only have 50 people to work with. So like I say, well, I don't want to work with a 24 cider. I could break that down into a smaller piece. This is how we do it. So, in order to calculate the mask per octet, we're going to turn the bits on always from left to right. We're going to start to left and move to the right. We're not going to go back and forth. Now, if we're at the address, we can go back and forth all over the place because that's how we get 192, 128, 10. But for mask values, they have to turn on from left to right only. So what we're going to do is we're going to turn on each bit one at a time and then calculate as we go across. So the first bit we're going to turn on is this one, and I already know this is 24. That means this, and this are full. 8 is 24. That's pretty good math.
How do you calculate that?
I just turn that one on and turn these off. And the decimal value is 128. The mask value for this octet is now 128. Remember we did base 2?
Mm-hmm.
And each of those base numbers has a decimal value?
Uh-huh.
These are those decimal values per bit position. So this is decimal value per bit position. That's all it is. It's a decimal value given the position that it's in. And this sequence will never change because it's after version 4. So in order to get the mask, I simply turn on the bits left to right one at a time. I turn this on, I keep these off. The value of my octet is 128. That means my mask value is 128, which means that would fit right there. Well, not there, but on the mask value. I'm now going to turn on 2 bits, 1 and 2, keeping these off. My accumulated mask value now is 192. So I added this number and this number. You look bored. Okay, good. You want to teach it?
Mm-mm.
Okay. Okay, so now we've got a new mask value. Because these 2 bits are turned on, I'm concerned with this column. And the octet has a mask value of 192. Just with 2 bits that are on. Let's do the pattern. 3 bits on, the rest are off. 128, 64, and 32 mathematically add up to 224. Okay, well, there's the pattern. Then there's your magic number, 255. An octet in active version 4 cannot have a value higher than 255. It's not possible. If you get a 256 or higher, you did something wrong. The chart didn't. You did something wrong. So again, turning each one on one at a time, left to right, the values accumulate for the mask. And so earlier we did default values of 255 for class A. That means in the mask, all bits were on in the first octet. So we just did this here. This is my 4th octet. That's scribble for octet. When we did a class B, we did the same thing, except we did it octet 1 and octet 2, and we got 255, 255 as a default mask. And then we did the same thing for class C, because this is my default cider. We just did this here, here, and here. Now there's a reason why we're doing it here, because part of what you need to know is you need to know some basic subnetting. There's basic subnetting, which means I'm going to break this down into smaller groups. This is a large group. I need to be able to break down the smaller groups. And we can do that. Okay, so all we've said so far is that the cider counts the number of bits that are on. So if we start with 24, which is the 24th bit, this is the 25th bit, there's all my bits. Remember we said earlier there's only 32 bits? There they are. Now we can physically see them. So, per column, that's why I said that if we have an octet value, it has an equivalent cider value. They say the same thing, but they say it differently. But that's how you find them. The only difference here is the range of bits goes from 17 to 24, 9 through 16, and 1 through 8, depending on which octet you're in. Just numbers. Right? They're just numbers. Okay, but I'm going to erase this because I don't want to confuse you all. So I'm only concerned with the 4th octet, because if you're tested on anything, You're only going to be tested on a Class C, and you're only going to be tested in the fourth octet in terms of a subnet. Tell me when you're with me, because you ain't with me just yet. You're like,
Just quick answer. Could you have a Class C network with a
yes.
CIDR less than 24?
Yes.
Okay, that's all I needed to know.
Okay. Okay. This gives us the maximum CIDR above my line. Host count. No host means number of IP addresses in my network. Minus 2 equals usable. Net scribble for usable. Host and subnets. The host count is the same thing as this, except I'm not going to start at 1, I'm going to start at 2. So if you were to be asked, and this is how this works, and this is where it gets a little bit tricky, but once you get it, hopefully. So I'm going to go back to my address. That's my network. I gave a default value so we know exactly what my network ID is. What's my network ID? Class, what's my network ID? This is I gave you this information. What's my network ID? Huh? What's my network ID? My network ID is 192.168.10.0, right? That is my ID. That says this is a group of IP addresses. It's all it says. This is a group. And I'm going to identify it by this number. I need a broadcast. I need to know where that network, that group stops. Very last IP address. That group stops at 192.168.10.255. I said that's my magic number. I can't go over it. My very last IP address. Now, who here has 256 fingers and toes? Because you got to count. You have to count and get here. Otherwise, you got to trust me. There are 250. This is 256 IP addresses, including the ends. Why do you know that? Because yours are 255 right there, and that's just another one. So add 1 to 255 to get 256. Do you trust me now? Okay, cool. But I said, well, that doesn't make any sense. Well, in the structure, this is counting the number of actual IP addresses in my network, the number of people in my group, the number of machines in my group. It's right there in my chart, so I know I'm right. I'm not smart enough to develop the chart. I just learned how to use it. That's why I teach it, because it works. Now, I've already said that we can't use 2 of those IP addresses. We can't use these 2 to put on a network machine. Whatever it is, can't use it, because this one identifies the network and this one's the broadcast, right? You said that already. Nod your head, because I know I said it. So we use the term usable. How many usable IP addresses do I have in my network? Well, I take that number and I subtract 2, and there's my 2. So I have whatever that number is, 254 for this case. So if you have a 192.168.10.0/24, there's my slant 24. I go to my next column, look for the IP count or my host count, and that's going to give you 2 things: the number of IP addresses in that network, the number of usable IP addresses in that network. This is chart 2. So it gives you everything. The chart gives you everything. And of course, that usable is the range. So my range of addresses is right here.
So, it's not like doing, it's like doing an inventory or what you can use?
Accents kind of thing. Say it again.
Is that like doing an inventory of the IP addresses you can use?
We don't use the word inventory, but you are right. We just don't use that word.
Okay.
We use the word range.
Okay.
Okay. So yeah, everything here I could use. I can use. I could put it on a phone. I could put it on a switch. I could put it on a router interface. I could put it on a server. I could put it on a virtual machine. I could put it anywhere I want to. It's usable. These aren't usable. We just use the word range. We don't use the word inventory in this context. I said this part duplicates per octet. This part duplicates per octet, but you gotta know what octet you're in because 32 is max, 25 is started the 4th, 17 through 24, 9 through 16, 1 through 8. Remember, it's just kind of number of bits that are on. Okay? This number, depending on where you want to be, this is just for your information now, not for test purposes. But say this was a 172 to 168, 10. We went to 168, and we'll just put that at 16. Say it was a class B. We duplicate these values in the 3rd octet. We run these numbers continuously. 248, 16, 32, 128, 256, 512, 1024, 2048, 4096, 8,000 something, 16,000 something, and we keep on doubling that number. That's why when I said that we were in a class A, there were probably 4 million addresses, because that number constantly doubles. And if my starting point is way over there in my 2nd octet, that number is extensively large. This is extensively small in terms of numbers. We could get smaller. But, so if your starting point was in the 3rd octet, 2nd octet, even in your 1st octet, because you could have a slant 3. Yeah, you can have a slant 3. 65 million addresses. The number just doubles. FYI, not testable at this point for you guys. Yes, cool. I want to subnet these. I want to break this larger. I want to break this 24. I want to break it in half. I want 120 people on one network and 120 people on another network. I can do that. I use the same numbers. I'm just going to start from the left to the right. Give me a time count. What time is it?
10:31.
Cool. I stop here. I wouldn't if I was in the 3rd or 2nd. I would just continue to double my numbers. But once I get to the end, I can't do it anymore at this level. I'll stop there. I can't subnet anything beyond that because I need at least 4 addresses. At least 4 addresses. I need 2 to use, an ID, and a broadcast. I need at least 4. There's ways to finagle that with Cisco equipment, but that's beyond the scope. So I need 4 addresses. Well, that's even a bit beyond now. I want to subnet. When somebody says subnet this, just break it in parts. That's what a subnet is. It's a smaller piece of the whole. So if I had a large pizza, and I give it to the 4 of you, I'd cut it in quarters. So you all have the equal share, hopefully. I can divide my network by 2, by 4, 8, 16, 32, 64. Equal pieces. So I would have 2 equal pieces, 4 equal pieces, all the way up to 64 equal pieces offering 4 IP addresses in it. Just from this. I'm not going to ask you to do that because you probably won't be asked that in the test, but we at least need to cover these two, so you get the idea. Okay. I'm going to do the 2. I always like doing the easy part, and I like to give the hard part to you guys. See if you understand the concept. All right. I'm going to break the 192.168.10.0 into 2 networks, 2 smaller networks. So the only thing I'm concerned about right now is this column and this number. That column is going to give me all the network information. That number is going to give me all the IP information. So I'm going to separate this because I'm dividing by 2. So this, everything to the left of this line is network information. Everything to the right of this line is IP information. And the only number I'm really concerned about is right there. Okay, so if I know that my focal point is just this column, I can do everything I need to do. First thing I need are my network IDs. I need to find out where my starting points are. Well, my first starting point is going to be right here. And what's my second starting point? That's my second starting point. This row becomes or will identify what I call my increments. So back in grade school, my daughter now is 9 years old. She can count by 1s, by 2s, by 3s, by 4s, by 5s, and by 10s rather efficiently. As adults, in the IT world, you need to be able to count by 128s, count by 64s, count by 32s, 16s, 8s, and 4s and 2s, and low ones. So this time we're going to count by 128. Those are my 2 networks. It's right there in the chart. It's right there in the column, and that's the number I'm looking for. Remember, decimal per bit position, mask, CIDR, host, subnet. The rows identify what we're looking at. The column identifies my network, because I'm subnetting. I'm subnetting by 2. I've got 2 networks. If and only if certain things now occur. I no longer have that because this tells me I've got 256 IP addresses. If I divide 256 by 2, I get 128 IP addresses. Minus 2 usable. And so I only have 128 usable addresses, 0 through 127, and then 128 to 255. So I've got my networks and I've got my broadcasts. If and only if what? If and only if my CIDR is 25. Just numbers. Just numbers on a chart. It can't be 24 because I said I want to divide that in half. I'm really dividing that number in half. And I did. Half of 256 is 128. There's 128 IP addresses here. There's 120 IP addresses there. Minus 2, usable, 126. So my range of addresses is .1 through .126, .129, 254. Network ID, broadcast, range, CIDR, mask. I got all 5 things. And I found them in my chart. I'm gonna go use the bathroom. You guys can work together. You're gonna create 4 equally divided networks from the same starting point. I'll be right back. I'll leave that up for reference.
Do y'all both fully understand the charts?
I think I understand it for this function. I'll tell you that like, I've looked at this a few times and I'll look at it and it'll be like, well, that's, okay, I get it. And then you kind of step away from it and you come back to it again and you're like, oh, wait, that was, that, I didn't get it. So what he's asking us to do, what is the network?
Uh,
192, 168, 10, 0. That's the network. And then the mask is what?
Oh, the mask is
Because the cider's a 26, so what's the mask?
The mask is 192, right? In that column?
The mask for,
The mask for cider 26, isn't it 192?
yeah, that'd be the mask. 26, that's not real.
yes,
The mask is 192.
yes, so 255, 255, 255, 192. That's the mask, right? Cider 26?
I'm back for the camera. Is that a question
And
for
now
me or
we're
for you?
carving it into, no,
Okay.
no, we're just working it out.
Okay, hash it out. Good. Can I erase this part?
Yes.
Okay, cool.
And so now cider 26 would carve that network into how many pieces?
Again, is that a question for me? Is that a question for me?
No,
It
that's
says four pieces. because we're
4
dividing
pieces,
by
right?
four. So 192 divided by 4.
right. And so then, like, how many pieces were there initially? How many total pieces are there? Or how many individual bits are there? How many individual potential?
Both.
Because the number you're starting with is 256, right? So you're dividing 256 by 4. So initially when you divide it, you're getting 128, right? When you divide it by 2, you get 128. And now you're dividing that 128 in half. And each of those is 64, right?
Mm-hmm.
So you've got a break point, you've got a 0 to 64, you've got a 64 to 127, and then the next break point would be 64 above 128. You guys following me or no? You have to divide, you have to figure out, if you stack 256 blocks, you have to figure out how to break them into 4 equal pieces. So how many blocks do you put in each group?
We do this.
64,
We call it long division.
right? So the first block, you got your first 64 blocks, and then your next 64, and then your next 64, and your next 64. And as you add them up, you've got 64, 128, 192, 256. So that is where you're picking your 4 bins. So to sit down, so do the math now for where that starts and stops for each of those groups. Because remember, you don't start at 1, you start at 0. So where are the 4 groups?
It's almost over. Got like 20 minutes of sleep time. And that's for those who are on camera and for you in the classroom, in case you just need to get to me. McNally, Keith at erau.edu. Identify yourself as an MSA candidate, because otherwise I wouldn't have your address. And for those of you in the virtual world, make sure you identify me as doctor. I fully appreciate it. All right, so what's the answer? We're breaking it down in 4 pieces. All right, well, there's my long division, so I don't need that anymore. And we know our starting point. This will always, whatever address you're given to start your breakdown will be your starting point. So we have a 0 network. 192.168, 10.0. I want to erase that because that's just in the way now. I need more room, so I'll go up here. We need a network ID and a broadcast. We need a network ID and a broadcast. We need a network ID and a broadcast. And one more for good sake. Okay, so I heard some logical thought. So let's start from the beginning. 192.168.10.0. Except this time we're dividing by 4. Okay, so I said, well, you already did the math, and we know that in order to divide 256, which is our starting point when we have a set of 24, you could do it that way, but I'm looking at this number right here. That's going to be my increment marker. I will increment by 64, which means my next network is 192.168, 10.64. My next one is 192.168, 10.192, 192.168. Is that right? No. Sorry. 128, 192. So I have my 4 starting points. Always start with your starting points, because I can find my ending points easier that way. Your ending point will never be a part of the other network. It can't be. It's an endpoint for another network, so I can't be in this network. And of course, we get our magic number, 192.168, 10.255. If and only if what? The decider is 26. That's the only column I'm looking for. This has to be consistent all the way through, because I took one network address and equally divide it by 4. That's all I did. So the decider has to be the same. And if we know the decider, by default we know the mass. 255, 255, 255 dot 192 is right there. And then we know the range of usables. Dot 1, dot 62, dot 65, 126, 129, 190, 193, 254. That's as far as any subnetting that you would be responsible for at this point in time. Now, to walk away, there are some other things that I'm not going to review, but you need to know, so you need to study on them. Services, primary services in your domain or network. Or things that you should know to do. We've already mentioned one of them, ipconfig. ipconfig is your command at the command prompt, or /all. This gives you some basic information. This gives you some more information. It's going to give you the IP address. It's going to give you the gateway address, and it may give you the DNS server address, depending on whether or not it's statically configured or DHCP configured. But in order to receive that information, and it will give you the physical address as well. But to get that information from the command prompt or PowerShell, you're going to type that in. At this point, you're going to learn some other things in the classroom. That's just my prompt. To test connectivity between machine to machine, you're going to run the ping command plus an IP address. So say we're going to ping to connectivity from 192.168.10.10 to 192.168.10.54. We'd be at the 10 machine, and we're going to ping the .54 machine, 192.168.10.54. We enter the ping command. If we wanted to route, if you wanted to know all the routers it goes through to get from point A to point B, you'd run the trace route command. It's short for trace route. Trace RT, trace route. Netstat. These are some commands. Find your network information. Services you need to know about. DHCP, Dynamic Host Configuration Protocol. Like I said earlier, you can manually do it. You could go into the network adapter and statically configure the IP address for that machine. The bigger the scale, the larger your network is, that's a tedious job. So we give that job to a server. That's your DHCP server, Dynamic Host Configuration Protocol. If you have a young girl between the ages of 0 and 16, they know about Dora the Explorer. I know I do. You need to understand what the Dora conversation is. That's what we call it. It's what allots a machine to receive. There's actually what we call the discover, the offer, the request, and the acceptance. 4 basic steps. There are other steps, but there are 4 basic steps that when you plug a machine in to the network and you configure for DHCP, that means it's looking for the DHCP server. It's going to go through this process. Okay? There's something called the PIPA, hopefully this is spelled correctly. I forget what the acronym stands for, but if this conversation fails, your machine will still give itself an address because it doesn't like to be isolated from anything, kind of like people. However, this address is 169.254. So if you see this 169.254, that means this failed. If you see nothing, when you pull up the IP config and you see nothing, it's not configured for this, and no static IP address was given. So if you don't see anything at all, it's configured for static IP addressing. That means you need to go in there and give it an address. If it's configured for dynamically receiving an address, and this fails, that means it doesn't reach the DHCP server, it will give itself somewhere in here. It will give itself a 169.254, and it will literally run the algorithm for anything. It could be anything within this range. 16,000 addresses. This is the DHCP service. Domain name system, or the domain name service, we're mostly accustomed to when we go surf the web. It still works within your enterprise network. So instead of memorizing every machine's IP address, you might just label things as your domain controller, DC1, or host 1 or host 2, depending on what's going on that machine, or the DHCP server. Easy enough, right? DHCP server. So if you want to make sure that you get to that, or you might be running IIS, Internet Information Services, within your network. So you're running a web page inside your network that people can access, so they can find information inside your network. Things that would be appropriate at this point. Protocols that you should be familiar with: file transfer, simple mail transfer protocol, telnet, secure shell. These are remote access protocols or services. This is not encrypted. This is encrypted. There are others, but if you start there and you use your study guide. Students who were successful at this within 1 or 2 tests, study beyond. So if you're studying for CCNA, or your Net Plus, your Network Plus exam, if you understand those concepts, this is nothing. So if you're studying, like if you study beyond what you're supposed to know, if you study just what you know, you might miss a couple of things. If you study beyond, you'll pick up everything. People on YouTube that you should become familiar with: the networking doctors, all contiguous characters. The networking doctors, and that's scribble for doctor. And I think they also have a website, thenetworkingdoctors.com. But if you go to the networking doctors, the first thing you'll see this big, massive guy who's bald. Looks like he bench 1,000 pounds. Looks like the Hulk. I mean, this is a massive dude. He's a CCIE, certified Cisco Network Internetwork engineer. The elite of the elite in Cisco. He's also a Microsoft certified trainer, as I understand it. The networking doctors on YouTube. Some people like to go to Professor Messer. I think it's spelled Messer, M-E-S-S-E-R. I think he's also bald. I think all of us IT people go bald. Not the ladies. Professor Messer, his are more classes. He'll like talk to you about definitions and concepts rather than talk to you how things work. So I've never really cared for him. Excuse me, Professor Messer, but other people do like you. So he's got a good following. Eli, the computer guy. Eli, the computer guy on YouTube. He breaks it down. I've always enjoyed his. I'm not sure if he's doing anything new. I know he's done some Server 2016 stuff, Microsoft Server 2016, which is what we're going to be studying. So he does. So some of that stuff is relatively new, within a couple of years. But all the fundamental stuff, maybe 5-6 years old, still relevant. So if you really appreciate his personality, the way he teaches his classes, Eli, the computer guy. Not sure where these guys are. I'm sure they tell them, reveal that stuff in their videos. I know he's up in Maryland. I think that's where he lives. He lives up in Maryland. Eli, the computer guy. And if you really want to break down and do this stuff in either a lab, virtual, or real, Dan's courses, all contiguous characters, Dan's courses. And again, these are all on YouTube. Dan, you won't ever see his face. You'll see his face, and his face. Dan doesn't reveal his face. He's anonymous. But he will go into Packet Tracer, which is a Cisco tool to build and configure and test labs, network labs. He'll break this stuff down for you. So services, how they work, how machines talk to each other, IP addressing, all that stuff. So these are go-to people for this type of information. I myself don't have anything of value regarding this because outside of doing this professionally, I teach them online as a hobby and hopefully as a new career. Otherwise, my focus is from 8 to 18-year-olds. But in the classroom here, on the recording, this is all good stuff. This is going to get you a starting point in the MSSA classroom, if that's where you want to go. If that's where you want to go and you want to start a new career, I can help you get there. Keisha and I work well, and Caitlin work well as a team. I do the academics. Jen's going to hook you up with professionals that get you the resume writing, the interview skills, the hiring events, all this kind of stuff. And I'm going to bust your ass in my classroom so you learn the material. Do you know how to stop the recording? We'll see you. Take care. See you next time.